In this video, I'm going to talk about molecular geometry, which is really all about molecular shapes. Molecules are three-dimensional. They take up space, they have volume, and the shape of a molecule does affect the physical and chemical properties of that substance. So molecular geometry, or the shape of the molecule, is something that we can predict from Lewis dot structure. Remember that as we were talking about Lewis dot structures, that most atoms in compounds have access to 8 valence electrons, the octet rule. One exception to the octet rule is hydrogen, that only needs access to 2 valence electrons, and there are some elements that have other arrangements so far as valence electrons, but they're not ones that we're going to cover in this course. These 8 valence electrons in covalent molecules are going to be arranged as pairs. They're either going to be pairs in a bond or a lone pair outside of a bond. And these electron pairs repulse each other. They have the same charge. They're all negatively charged, so they don't want to be close to each other. They want to be as far apart as possible. The way that the repulsion between different electrons affects molecular geometry is put together in something called the VSEPR theory, or the valence shell electron repulsion theory. And the basic premise is that each electron pair, whether it is a lone pair or a shared pair in a bond, wants to stay as far away from every other electron pair. The best shape for arranging 4 pairs of electron is what is called a tetrahedral shape, or a tetrahedron. And you can model that by taking 4 balloons and blowing them up and then tying them all together in the central. So that would be your central atom. And we imagine that 4 bonds are going off from that. So if you think about, try to picture what that's going to look like, the 3 balloons on the bottom are going to roughly take up a triangle shape, and then there will be a 4th one going, pointing up to the ceiling. So it ends up being a pyramid that has a triangle base, and that's a tetrahedron. And so every bond coming out from this central atom will be on one of these lines. We'd be a bond coming straight out at us and a bond going straight up pointing to the ceiling, and then one going to the back one way and one going to the back the other way. Now, there are more than the situations of molecules are not just 4 bonds, but there are other possibilities involving lone pairs as well as bonds. And interestingly, lone pairs are actually more repulsive. They have stronger repulsive force than the electrons in bonded pairs. And so this is actually going to change the tetrahedron so that you don't have this shape for every single molecule. There are many shapes that are possible, even though you're talking about 4 arrangements around a central atom, for kind of 4 places that electrons can be. But let's start with this tetrahedral. What arrangement of atoms is going to cause that? Well, a tetrahedral shape comes from a central atom that has 4 areas of shared or electron bonds around that atom. And the distance between each of those bonds, or the bond angle, is 109.5 degrees. So between these two is 109.5, and between these two is 109.5. So it's all 109.5 because it keeps everything as far apart from each other as possible. An example of that would be methane, or CH4. So carbon, if you remember, has 4 valence electrons, and it will bond with hydrogens for each of these spots. So we're going to have a bond coming off between carbon and 4 hydrogens. And so this Lewis dot structure is a 2-dimensional drawing, but 3-dimensionally it will look more like this shape over here, which you can't see very well because I've drawn all over it. But if I erase things, you can kind of picture what this would really look like if it was sitting there on your table as a 3-dimensional shape. We've got carbon in the middle and then hydrogen out in these 4 directions. And that's your tetrahedral shape, or tetrahedron, the shape that you get with a central atom and then 4 bonds coming out from that atom, or 4 areas of shared electrons. What if you have a central atom with only 3 areas of shared electrons? Well, here your bond angle is going to be different than 109. In fact, it arranges as an equilateral triangle, so the bond angles end up being 120 degrees. An example of this would be formaldehyde, which has the formula CH2O, And the Lewis dot structure for this, we have a double bond between the carbon and the oxygen, and then a single bond between the carbon and the two hydrogens. Oxygen does have lone pair of electrons, but the lone pairs only matter when they're on the central atom, so the carbon will not have any lone pair electrons to affect it. So we just have 3 areas of shared electrons because this double bond is counted as 1 area of shared electrons. And so it arranges itself as this trigonal planar shape. So it kind of looks like, a triangle. That's where the trigonal comes from. And it's flat, like a plane. It's also possible to have 3 areas of shared electrons around a central atom and 1 lone pair. And that will make a difference because this lone pair will push the bonded pairs closer together. This creates a situation where the bond, instead of being 109.5 degrees like we saw with a tetrahedron, but this bond angle will be 107.3. So it's just a tiny bit smaller. That's because there's lone pair electrons here, and they are exerting a repulsive force down on these shared pairs of electrons that are in the bonds. So it kind of, instead of having a flat base like the trigonal planar, where it'd be like flat on the table, it's lifted up a little bit. And so that it has more of a pyramid shape, so it's a pyramidal shape. An example of a molecule that would have a pyramidal shape is ammonia, NH3. Remember, nitrogen has 5 valence electrons, and so with our 3 hydrogens, they're going to bond in these 3 places, and then the lone pair taking up that 4th side. And again, this is your 2-dimensional Lewis dot structure, and then our 3-dimensional picture over here. Now we're working down to a central atom with only 2 areas of shared electrons and 2 lone pairs, which again are going to push the bonded pairs closer together. So our bond angle is going to shrink even further. We went from 109.5 to now we're going to have 104.5. And again, we've got these these lone pair electrons that are exerting repulsive force down. We've got kind of like double whammy of 2 of them pushing down to shove the bonded or the shared electrons together. Water is the classic example of a bent molecule. And so again, oxygen has its 6 valence electrons, looking to make 2 bonds, which are easily done with these 2 hydrogen molecules. And so we can see in our Lewis structure the shape that's going to be translated into a bent molecule when it comes up 3-dimensionally. And then finally, a linear shape comes from a central atom with 2 areas of shared electrons and no lone pairs. And so the bonding pairs will arrange themselves on opposite sides to be as far away from each other as possible. Thus, that gives you a bond angle of 180 degrees. An example of that is carbon dioxide, CO2, which I forgot to write here. But of course, our carbon is double bonded to oxygen. Even though there are lone pairs on the oxygen, there are no lone pairs on the carbon, and so it puts out a linear or a straight line molecule, which keeps those shared pairs of electrons as far away from each other as possible. There are other shapes. Here's just 2 of them, a trigonal bipyramidal. So basically it has a trigonal center. It has a triangle in the center and then a pyramid off either side. And then an octahedral has a square in the center and pyramid on off the other sides. So these are more advanced shapes than you need to figure out in this class, but just wanted to give you a heads up that they exist. So what do you do to determine the molecular geometry? Well, you draw the Lewis structure like I've been doing as I'm going through this video, and then determine the number of bonded pairs and lone pairs around that central atom and use that to determine the molecular geometry of that particular molecule. You will have your notes to refer to help you figure this out as you're working through the problems in class. But just for an example, let's take phosphorus triiodide, Pi3. So phosphorus on the periodic table is here below nitrogen, which means it's going to have 5 valence electrons. So our phosphorus is going to look like this with its valence electrons. And then each of our iodine molecule or iodine atoms is going to have 7 valence electrons, and so it just needs 1 to make the bond, and then the other 6 are lone pairs on the iodide, but that doesn't matter because the lone pairs on the atoms that are not the central atom do not count. They do not affect the shape. So you're only worried about lone pairs on the central atom. So there's only 1 lone pair. There's 3 areas of shared electrons. And if you go back through this video, you'll see this is our pyramidal shape. So the molecular geometry for phosphorus triiodide is pyramidal. So again, just practicing this is the best way to get a handle on molecular geometry. We're working with very simple molecules here. There certainly are more complex shapes, but you won't need to worry about them for this class.